So, a reminder that we have our exam Monday through Wednesday. And so our Zoom question and answer session tomorrow morning at 10. And that the link, I emailed the link out to you, so you already have the link for that. We're going to record the topic outline later this afternoon, so that should be posted by about 6 today. So hopefully you have a chance to look at that before the Zoom session Saturday morning. So today we're going to start chapter 29, which is carbon-carbon bond forming reactions. That's a very broad topic. We're going to focus specifically on organometallic reactions involving transition metals of some type for the most part. Not all of the reactions will involve them, but the vast majority of the ones in this chapter will involve transition metals. So we'll go into a little more detail than the book does on palladium chemistry, because two of our most important reactions, including the Suzuki coupling that we'll talk about today, involve palladium. So we'll need to learn a little more about transition metals. So this chapter used to come directly after the amines chapter in the older editions of the textbook. And then when they came out with this edition, they shuffled the chapters a little bit. The reason we're keeping it in this particular order is that the reactions we're learning in this chapter are very widespread in modern organic synthesis, okay? Particularly the Suzuki coupling, the Heck reaction, and the alkene metathesis reaction. These reactions are very widely used. Their discoverers have won the Nobel Prize, and so because we just gave you a synthesis assignment, and you'll be looking in current literature for multi-step syntheses, there's a very high probability that you will see the reactions in this chapter in those syntheses. So it's beneficial to you for that synthesis assignment to have this chapter earlier in the semester rather than later. So we're keeping it in the original order, which is coming right after chapter 25, as opposed to being postponed. Now, we could spend an entire semester talking about transition metal chemistry, organometallics, and how transition metals are used in organic chemistry. Indeed, we do have a course for graduate students that's an entire semester that focuses exclusively on transition metals and their chemistry. And we're just going to have 2 days. So what that means is we will cover the topic in more detail than the textbook does, but it'll still be very, very superficial, okay? So as a result, there will be a few concessions in regard to what material from this chapter would appear on the exam. Okay, so you won't see challenge level problems involving this, this material, because we'll only be able to cover it at a basic level. We're also not going to be able to learn how to link these reactions to other reactions we've learned in the class, because we're very limited in what we can teach you about how to prepare the precursors for some of the reactions in this chapter. So as a result, you're not going to see the reactions from this chapter on a synthesis problem on the exam, okay? So you won't see it on synthesis problem. You won't see challenge level problems coming from this chapter. However, you certainly could be asked to draw any of the mechanisms that we're going to go over. So you need to learn the mechanisms in this chapter. You need to be able to predict the products. You need to be able to provide the reagents. You need to be able to have a fairly basic understanding of the principles we're going to talk about today. So a few concessions due to the fact that we don't have unlimited time to teach you organometallics. But please do not ignore this chapter, right? Students who ignore this chapter and focus on just the other 3 chapters are usually disappointed with the result when they take this exam. Any questions? Okay, then let's launch into our first reaction in this chapter that forms carbon-carbon bonds and involves the use of organocuprate reagents. These are reagents we've learned about previously in class. We've learned that organocuprates react differently than Grignard reagents and organolithium reagents. We've learned that they react with acid chlorides to form ketones. We've learned that they react with alpha-beta unsaturated carbonyl compounds, and they react at the beta carbon. So they add to the alkene and not to the carbonyl. And now we're learning a third reaction of these organocuprates, and that is a coupling with various types of halides. Okay? So we can take a primary alkyl halide, a vinyl halide, or an aryl halide, and then in some cases, secondary alkyl groups. That's kind of the borderline of reactivity, where tertiary alkyl halides are too bulky and hindered, and they don't react with organocuprates, but secondary alkyl halides in some cases will. And the requirements for the groups on either the halide or the cuprate are the same. Okay, so the group on the halide can be primary, vinyl, aryl, and in some cases alkyl. The group on the cuprate can also be in these same categories. And what's going to happen is we're going to form a carbon-carbon bond between those two groups. And then these are the byproducts that we're going to get from that reaction. Okay? So there's a variety of possibilities where this reaction can be used, but the most common ones that you'll see, the ones that you see in the book, the ones that you most commonly see in the organic chemistry literature, involve forming a bond between an aryl or vinyl group and an alkyl group. Okay, so connecting an alkyl group to either an alkene or a benzene ring. That's what this reaction is most commonly used for, and those are the two examples I've drawn for you on the board. And because the groups on the cuprate and the halide are interchangeable, you could have an alkyl halide and an aryl or vinyl cuprate, like we do in the top example, or you could have a vinyl or aryl halide and an alkyl cuprate. Either of those combinations works. Okay. One other feature that the second example shows us is that these reactions are stereospecific, meaning that a specific isomer of our alkene, whether it's part of our cuprate or our halide, will give a specific isomer of the product. And in this case, the stereochemistry of our alkene is retained. You can see this is a trans vinyl bromide, and we end up with a trans alkene in the product once we form the carbon-carbon bond between this carbon and that carbon. Okay? So, as I've mentioned, because the structural requirements for those R groups on the cuprate and the halide are identical, you have two possibilities to construct a given product by an organocuprate coupling reaction, and either of those possibilities will work. So this is more like reductive amination, where we said both possibilities will work, than it is like the Wittig reaction, where only one of the two possibilities typically works. And this sample problem here on the screen shows us that. We have this target compound, 1-methylcyclohexene, and you can see that there are two possibilities for making it. We can use either the dimethyl cuprate and the vinyl bromide, or we can use the dicyclohexenyl cuprate and iodomethane. Either of those would work. The other thing this sample problem shows us is it reminds us how we synthesize the organocuprates, and we start from halides. We convert a halide into an organolithium, and then we react the organolithium with copper iodide. So ultimately, we're starting from two halides, and we convert one of those halides into the cuprate, and then we couple it to the other one. So essentially what we're doing when you add in the synthesis of the organocuprates is we're taking two halides and we're coupling them together and forming a carbon-carbon bond. We're not doing it directly. We have to convert one of them into a cuprate. Okay, any questions? So I told you that either of these pathways would be fine. On an exam, they would be fine. In the lab, you would probably go with possibility number one, because if you look at the stoichiometry of the reaction, only one of the two R groups from the copper gets transferred to the product. One of them remains in a byproduct. And you probably rather waste your cheaper, one equivalent of your cheaper halide, smaller, cheaper halide, than your bigger, more expensive halide. But that, for purposes of an exam, we would we would consider those to be equivalent to each other. Okay? So, in regards to the mechanism of this reaction, we can tell you definitively what it is not. We know that it is not SN2 because of the fact that you can use aryl and vinyl halides. Okay? Unfortunately, we can't tell you much more than that. This is a complicated area, and it is. There's been a lot of debate amongst organic chemists who care a lot about mechanisms over the past few decades. And so the likelihood is that there's more than one mechanism operating simultaneously and that it is complicated. So we're going to skip that because we don't have much time to discuss these topics. So we're not going to learn the mechanism. We are going to learn that it is not SN2, and we're going to learn the key detail that it is stereospecific and that the configuration of the alkene is retained in the product. Okay? Any questions about our organocuprate reactions? Okay, so the next reaction we're going to talk about is the Suzuki coupling. But before we get into the Suzuki coupling, since it is a reaction involving palladium, we're going to spend some time giving you a brief introduction to palladium chemistry. The book gives you an extremely brief introduction to it. We're going to go into a little more depth on it so that you have a little better understanding, still fairly superficial, but at least a little bit better understanding of palladium chemistry. So we're going to start out by looking at palladium's position in the periodic table. So palladium is a transition metal, okay? And so palladium, like all transition metals, does not follow the octet rule. A palladium atom is happy, satisfied, stable, whatever you want to say, when it has 18 electrons, not just 8. So why does palladium and other transition metals follow an 18 electron rule as opposed to the octet rule? Yes, please. Okay, so in transition metals, in the position of the transition metals in the periodic table as we're going across from left to right, we're filling the d orbitals. So the d orbitals are involved heavily in the chemistry of transition metals. Okay? So for a transition metal then to be stable, it has to have its d orbitals filled, not just its s and p orbitals. How many d orbitals do we have? We have 5, and so to fully fill them, we need 10 additional electrons beyond the 8 that are going to fill the S and the P. So that is why palladium, as well as all our transition metals here, directly under this title of our periodic table, are going to follow the 18 electron rule. So the column palladium is in is critical for its chemistry and is why it is useful very, very useful in organic synthesis. Unfortunately, this periodic table does not have the columns labeled, so we have to count across 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we see that palladium is going to be in our 10th column of the periodic table. So how many valence electrons does an isolated palladium atom have? 10, exactly. By virtue of being in column number 10, it has 10. How many does it want? It wants 18, so it wants access to 8 more electrons. How does it get access to 8 more electrons? Well, it binds to species known as ligands. Okay? Ligands are molecules that can coordinate to transition metals. Transition metals are Lewis acidic because they have these empty orbitals. And so these ligands are going to be Lewis bases. They usually have lone pairs that are donating to the electron, donating their electrons to the transition metals. So here on the screen, we have some examples of common ligands that bind to palladium. And you see they're all phosphine ligands. They have a phosphorus atom that has a lone pair. So that lone pair on phosphorus is donated to the palladium. And these are 3 very, very common phosphine ligands Triphenylphosphine is probably the most common one that you see bonded or associated to palladium. So there's some important things to understand about ligands. So as I mentioned, the interaction between a ligand and a palladium atom or other transition metals is best understood as a Lewis acid-Lewis base interaction. We typically draw that with a sigma bond, the way we draw Lewis structures, but it's certainly not as strong as a typical sigma bond, a carbon-carbon or a carbon-hydrogen or even a carbon-halogen bond, okay? So the coordination between a ligand and a metal is reversible. Okay, it can spontaneously dissociate and then spontaneously reassociate to the metal. So why do we need ligands? Well, we need them to stabilize our metals, right? The palladium, if it doesn't have those 18 electrons, it's going to be incredibly reactive and it's probably going to decompose. It's not going to hang around long enough to catalyze the reaction you want it to catalyze. So we need ligands to stabilize the palladium, to allow it to have access to those 18 electrons. But at the same time, to be able to dissociate, to be able to catalyze reactions. The ligands also impart solubility. Palladium is like dirt or brick dust. It's completely insoluble. And so if you want it to dissolve in an organic solvent, you have to have organic ligands coordinated to it that are going to bring it into solution. So you see a whole ton of carbon on these ligands. That makes the ligands and then the palladium complex to the ligands soluble in organic solvents. Okay? But it's important to note that these ligands are spectators in the actual chemistry that is occurring. They are not going to be participating in the steps, in the mechanisms that are happening. Their role is simply to solubilize and stabilize and then be able to dissociate when we need them to dissociate. Okay? Any questions on the roles of ligands in palladium chemistry? We're typically going to abbreviate them as L. That's a common abbreviation that is used for ligands. So what are some common palladium catalysts? So the triphenylphosphine is a very common ligand. And so if we have 4 triphenylphosphines around our palladium, how many electrons does this palladium have? Okay. How many does an isolated palladium atom have? It has 10. And then we add a lone pair from each of 4 phosphorus atoms. And what do we get? We get 18. So this is a stable complex. So our transition metals are reactive. They're generally not very stable. They're hard to hold on to. They're hard to store. But this complex, palladium with 4 triphenylphosphines around it, is stable. We can store it. So we can buy it from a supplier. They ship it to us. We can store it. We do have to keep air away from it. But this is stable enough that we can store, and then we can weigh it out and put it in a reaction when we need to use it. Okay. Yes, Brady. So we treat charges kind of loosely in palladium chemistry. If you're going by the rules of Lewis structures, yes, you'd put positive charges on them, but we don't do that when we're just showing ligands coordinating to metals. So the rules are looser than they are typically for Lewis structures. So another one, not all ligands are phosphine, so we can have acetate as a ligand. And so palladium acetate is another palladium complex that is stable enough to be shipped and stored. But instead of having 4 ligands around it, palladium acetate only has 2. And that's because you have 2 atoms in acetate that have lone pairs. You would have the negatively charged oxygen, which can donate one of its lone pairs. And notice we're not showing the negative charge. Again, the rules for showing charges are looser. We're not going to be able to get into them in this class. But then, typically, when you show the coordination of the lone pair from the carbonyl to the palladium, you usually use one of these arrows instead of a regular bond. And that's just showing you that that interaction is going to be weaker than the interaction between the negatively charged oxygen and the palladium. Okay, all of these interactions are weaker than carbon-carbon and carbohydrogen sigma bonds, right? But these ones shown with the arrows are weaker than the ones that we're showing here with the bonds. Okay, so again, we get 18 electrons because we're getting 4 electrons from each of our ligands here. Okay, now we're not going to get into oxidation state discussion very much of these metals. That's something we just don't have time for in this class. But these palladiums are actually at different oxidation states. In case any of you have studied this as part of your research, this would be palladium 0 and this would be palladium 2. But we're not going to get into that. All right. Any questions about our palladium complexes and the ligands? Another important thing about palladium is that it is used in catalytic quantities. It is going to be turned over or regenerated in its active form at the end of the reactions we're going to learn. And that's important because palladium is really expensive. So you would never want to use a full equivalent of palladium in a reaction. Not only is it expensive, it is rare. So we'd probably run out of palladium in the world if we were trying to use it in stoichiometric quantities. All right, so now we're going to talk about some common processes that occur on palladium catalysts in the course of organic reactions. And your book briefly mentions these and doesn't mention all of them, so we're still going to be brief, but we're going to go into a bit more detail than the book does when we talk about these processes. So the first one we're going to mention is called oxidative addition. So in an oxidative addition, our palladium can only have 2 ligands attached to it. L is the abbreviation that we typically use for ligands. And so 2 of those ligands have to dissociate. And as I mentioned, when you dissolve a palladium complex, there's going to be an equilibrium between the fully saturated palladium complex and ones where ligands have dissociated. Okay? And so if 2 ligands dissociate, that's going to be reactive. It's going to want to react. And when it collides with an aryl or vinyl halide, it's going to be able to react. Okay? So here's our aryl or vinyl halide. And what's going to happen is we're going to break the carbon halogen bond, and we're going to attach the R group and the halogen to the palladium. Okay? So our palladium over here only had 14 electrons. Right? Now we're able to get it back to 18 electrons, so it's happier. And we have attached our R group to the palladium, and that's critical for the reactions that we're going to see in this chapter. Okay, so this is called oxidative addition. The reason it is called oxidative addition is the palladium's oxidation state has increased by 2. Here it is 0, here it is +2. You don't need to know that in order to understand the chemistry we're learning in this chapter, but if you're curious as to where the name came from, that's where the name came from. The palladium is being oxidized in the oxidative addition step. Okay? Any questions about oxidative addition? So the other thing we're going to learn in this chapter is that these steps on palladium come in pairs. You have one process, and then you have a process that is essentially the reverse of that process. And so the reverse of oxidative addition is called reductive elimination. Okay? So reductive elimination is the second process on palladium that we're going to talk about in this chapter. So we're going to have a palladium complex that's similar but not identical to the one that is drawn here. Okay. So the difference is we've replaced our halide. This is usually a bromine or an iodine. We've replaced that with another aryl or vinyl group. We'll talk about how that's done specifically in the Suzuki coupling later on today. But once we get to this point where we have two aryl or vinyl groups, or sometimes one of these is a hydrogen, then what can happen is those groups can come off and be bonded to each other. Right? They come off the palladium and they form a sigma bond, typically a carbon-carbon sigma bond, but in some cases it could be a carbon-hydrogen sigma bond. And then we end up with our 14 electron palladium, which is going to be very reactive, and then be able to participate in other steps. Okay? So this is the reverse of oxidative addition. As you might have guessed, the palladium itself is what's getting reduced in this case. That's why we have that reductive term. It's going from the +2 oxidation state to the 0 oxidation state. Okay? And this step is usually very thermodynamically favorable because palladium carbon bonds are fairly long and weak. And then we're forming a carbon-carbon or a carbon-hydrogen bond, which is going to be short and strong. Okay, so we're forming a very strong bond at the expense of these two weak bonds. Okay? Any questions about oxidative addition or reductive elimination? Yes? So you're not going to do an oxidative addition into a carbon-carbon or a carbon-hydrogen bond. Those are too strong. So that's why we have oxidative addition only into the carbon-halogen bonds, because those are weaker. Okay, so typically the way it's done, the thermodynamics favor oxidative addition with halides, because you're breaking a weaker carbon-halogen bond, and you're generating two sigma bonds from that, right? Here you're breaking two sigma bonds and forming only one, but this one is so much stronger than the ones you're breaking that it works. So Le Chatelier's principle usually doesn't apply. It usually goes in the direction of oxidative addition with carbon-halogen bonds, in the direction of reductive elimination with carbon-carbon or carbon-hydrogen bonds. Okay? Good question. Other questions? Yes, Ben. The ligand will not be eliminated to form a bond, because the ligand usually is just using a lone pair and it doesn't want to form another sigma bond. It just wants to have that Lewis acid Lewis base complex. The ligands are continually associating and reassociating. So the picture of how many ligands are on the palladium is much more complicated than what we'll show you. But you don't need to worry about that. You can just write two ligands the way we did, put L, and then forget about the rest, as long as you know what they're doing, which is providing solubility and stability. Okay? One other aspect of reductive elimination that is important to remember is that it proceeds with retention of any alkene stereochemistry that is present. Okay, so much like we saw with the cuprates, the organocuprate couplings, it's stereospecific. And we retain the stereochemistry in the vinyl halides or in the cuprates. If one of these R groups is an alkene, if it's cis, it's going to be cis in the product. If it's trans, it's going to be trans in the product. Okay, so we're going to see retention of our alkene stereochemistry. All right, let's move on to our third process that occurs on palladium. This one isn't mentioned until later in the chapter, and they really skip over it. So we're going to give it a little more detail than what the book does. And that is going to be the alkene insertion. An alkene insertion is going to be an addition reaction. Okay? So in an alkene insertion process, we're going to have palladium, and then that palladium is going to have some sort of R group. It's going to have our two ligands. It's usually going to have a halide. So this typically has been formed by an oxidative addition process. And then after an oxidative addition process, if this palladium species encounters an alkene, it can perform an addition reaction to that alkene. And it's the palladium R part of the species that's going to add to the alkene, which means that palladium is going to be bonded to one carbon and R is going to be bonded to the other carbon, and we're going to break the bond between palladium and R. Okay? So I'm going to draw the product here for you. We're going to get palladium there, and there's still an X on there. Let me just fix that. Okay. And then we're going to get R over here. I'm actually going to show some stereochemistry for the groups on the alkene. Okay. All right, so we learned about many different types of additions in the class, and this addition is most similar to the hydroboration reaction. The hydroboration reaction was a concerted addition rather than a stepwise addition. We didn't have an intermediate, and that's the case here. This is a concerted process. There's no intermediate. We're going to break the pi bond, break the palladium R bond, and form the two new bonds simultaneously. Okay? And so when that happens simultaneously, we have stereochemistry associated with that. It's going to be a syn addition. In this case, it was a terminal alkene I showed you, so you couldn't really tell it was a syn addition because these two groups are both hydrogens. But the palladium and the R are going to end up on the same side of the alkene. Okay? But something else that's important about this alkene insertion or this syn addition reaction is that the palladium is going to bond to the more substituted carbon. Now that should surprise you. Right? This palladium is huge, and it has these giant ligands on it. Okay, so this is a massive group, yet it is bonding to the more substituted carbon. So the full explanation why is a little bit beyond the scope of what we're going to do in this class, but the simple explanation for why this happens is that this palladium-carbon bond is much, much longer than this carbon-carbon bond is. So even though this palladium is huge, it's much further away from this carbon than this R group is from that carbon. So the distance, and then the palladium ligand bonds are also really long. So these ligands are pretty far removed from this more substituted carbon. So palladium bonds to the more substituted carbon of the alkene because that bond is very long, and so it's actually much further away from the more substituted carbon than that R group is from the carbon it attaches to. Questions? Okay, so those are the two things to note here: syn addition, and the palladium ends up bonding to the more substituted carbon. But this is just an addition reaction, similar to a hydroboration. If you pretended that your palladium was boron and R was a hydrogen, it would be like a hydroboration type reaction. Okay? All right, so in the same way that we had a pair of reactions here on this, middle board, we're going to have a process that pairs up with our alkene insertion. Our alkene insertion is an addition step, so the reverse of that is going to be an elimination. And we're going to refer to that as beta elimination. It's often called beta hydride elimination because it's usually a hydrogen that is being eliminated in this process. Okay? So what we're going to have in a beta hydride elimination we need a palladium. We need an alkyl group attached to our palladium. That's what we have after an insertion reaction. Our alkene becomes an alkyl group because we've added to the pi bond. We have to have at least one beta hydrogen atom in order for this to work. Okay? And then you'll notice that we only have 3 things attached to our palladium instead of 4. That's also important. You cannot have 4 things attached to palladium for beta elimination to work. And then we're going to have various other groups. And in this case, we're going to put, actually, let's do it like this. Okay. So we have this species, we have a beta hydrogen, we have our palladium. You'll notice these are in the same plane and they're eclipsing with each other. They have a relationship that is known as syn coplanar, and that is vital. You have to have a syn coplanar relationship between your beta hydrogen and your palladium in order for this beta elimination process to occur. So what's going to happen is we're going to form an alkene. Elimination reactions form alkenes. So we're forming an alkene in this process. And so these carbons become the alkene. We're going to form a carbon-carbon double bond. Okay. So here's our product. You'll notice that in this syn coplanar conformation I've shown you, these R groups are trans to each other. And so they're going to be trans to each other in the alkene that we formed. Okay. And then this hydrogen that has left from this carbon is going to be bonded to the palladium. So the alkene initially is going to be a ligand for the palladium. The pi electrons in the alkene will function as a ligand to the palladium. Okay, but that's a weak interaction, and so that's going to fall off, and that's going to give us our trans alkene, and then it's going to give us our palladium catalyst, which is going to have a palladium hydrogen bond. In many cases, as we'll learn when we talk about the Heck reaction next week, you can actually reductively eliminate HX off of the palladium. But as far as the beta elimination goes, you end up with a palladium hydride species, and you end up with an alkene. Okay? And so the key things to note here is that you have to have this syn coplanar arrangement. So this contrasts to E2 reactions. E2 reactions, we have to have anti-periplanar. The hydrogen and the leaving group have to be anti to each other. In this case, because the beta hydrogen ends up bonded to the palladium, it has to be in this eclipsing or syn coplanar relationship. And then in this particular case, we ended up with a transalkene. If we were to have rotated about this carbon-carbon bond and brought this hydrogen up, that would have brought the R group back, and we would have gotten a cisalkene. Okay? We'll talk about that issue on Monday when we get into the Heck reaction. But you can see that you could get either a trans or a cisalkene, depending on if you rotated about this carbon-carbon bond in this particular example. Questions about beta elimination? Okay, so we're ready now to talk about the Suzuki coupling, our first reaction in this chapter, or first palladium catalyzed, first of the two palladium catalyzed reactions in this chapter. So the Suzuki coupling was named after Professor Akira Suzuki. He was at the University of Hokkaido in northern Japan. And this reaction is used very widely in organic chemistry. So as a result, he won the Nobel Prize in 2010. Periodically, there are researchers who survey the medicinal chemistry literature to see what reactions are being used the most to synthesize drugs. The number one reaction is always amide bond formation. There are lots of amides in drugs, and so amide bond formation is always number one. But the Suzuki coupling is always in the top 5 in terms of reactions that are used most widely to make drugs. It's just a very, very useful process, and that's reflected in the fact that Suzuki shared the Nobel Prize in 2010 with some other researchers. So in 2012, 2 years after he got the Nobel Prize, I was on a sabbatical leave at the University of Tokyo. And so as part of that, I had the opportunity to go to Hokkaido. One of my good friends is a professor there at the University of Hokkaido. Professor Suzuki was already retired by then, so I didn't get the chance to meet him. But they have a museum at that university. And as you might imagine, they have a big exhibit on Professor Suzuki and his research, because he's probably the most famous person that's ever worked at that university, having won the Nobel Prize. And it was interesting that they kind of have like a small version of his office. They have his desk and his typewriter and some other things there that I'm not sure if people are really interested in seeing. But they had a really cool display in which they were trying to explain to the average person, to a non-chemist, why the Suzuki coupling is important, why it was worthy of winning the Nobel Prize. And they were talking about how it can be used to make drugs, basically the same thing I mentioned to you. But to me, the thing that was most interesting and most neat about that is as an example of a reaction that's useful in making drugs, they'd actually printed on this display a reaction that I had done myself. Because when I was a graduate student, I've told you before, I worked on the synthesis of vancomycin. And in synthesizing vancomycin, we used a Suzuki coupling reaction. And they'd actually chosen that reaction to put on their display to show why this was a useful reaction. So I was pretty excited about that. That was a pretty neat thing to see a reaction I had done in this museum. So let's talk generally now about the Suzuki coupling. What are we accomplishing in this reaction? We're going to take an aryl or a vinyl halide. We're going to react that with a boronate reagent. We're using a lot of abbreviations here. We're going to define these R's and R primes and Y's in a moment. We're going to use a palladium catalyst. The most common one is our palladium. This is called palladium tetrakis triphenylphosphine. Okay. We're typically going to use about 5 to 10 mole% of this catalyst. Sometimes we can get away with less than that. We're going to need a base in the Suzuki coupling. We can use a lot of different bases, but sodium hydroxide is a common one, a nice simple base. And we're going to form a carbon-carbon bond between the aryl or vinyl groups that were part of our halide and our boron species. Okay? At the end of the reaction, we're going to end up with our base, which is often hydroxide, attached to the boron. And then we're just going to have a salt, a sodium salt with the halide we started with. Okay? So R and R prime are going to be either aryl or vinyl groups. Okay? They're generally not going to be alkyl groups. Now, there's more modern versions of the Suzuki coupling that have been developed more recently that will allow you to use alkyl groups in some circumstances. So if you're coming across Suzuki couplings as you're looking for your paper for the synthesis assignment, you might find some versions that use alkyl groups. Okay, so they exist, but the classical version of the reaction, which is what we're learning now, uses aryl or vinyl groups. Okay, and then X is going to be bromine or iodine. Okay? Vinyl or aryl bromides or iodides. Vinyl or aryl bromides or chlorides are more stable. That carbon-chlorine bond is stronger, so the oxidative addition is not as favorable. Now, again, much like I said with the alkyl groups, there is modern research going on that is allowing vinyl or aryl chlorides to be used. So there are some newer versions of the Suzuki coupling that will use chlorides, but the classical one we're learning in class uses bromides or iodides. And then Y, the groups on the boron are either going to be alcohols or ethers. Okay? So first, let's look at some of the products that you can obtain from a Suzuki coupling. Okay? So here's some examples. Here's some examples of the boranes that you see with these ethers. This is called catechol. This ortho hydroxyphenol species would be called catechol. This is a catechol boronate. And you see that, so you're seeing here, they're showing you the new carbon-carbon bonds that are formed. And you see that the alkene stereochemistry is retained just like it was in the organocuprate couplings. So here we have a trans vinyl boronate. We've got the trans alkene there. Here we have a cis vinyl bromide. So in this product, we have a cis double bond here and a trans double bond here. So you can see this reaction is very good for coupling alkenes to aromatic rings, or two alkenes together, or even two aromatic rings together, although that example is not shown here. Okay? But the important thing is the stereochemistry of the alkene is retained in the product. So you should be able to look at a vinyl halide and a vinyl boronine reagent and predict the product that you would get from that Suzuki reaction. So go ahead and get your eye clickers out, and please go ahead and talk to your neighbors and predict the product of that Suzuki reaction. All right. Let's try to get our final answers in. Next couple seconds. Okay. All right. We had a flurry of answers come in. Any more? Going once. Going twice. Okay. Which product is formed? B. Okay. So you notice that if you look at the product, you can see the part on the left is what's coming from our boron reagent. And since that has a trans double bond, we need the trans double bond here. And you see the part on the right is coming from the vinyl halide, and so that's cis here, so it has to be cis there. Okay. So I mentioned to you that the Suzuki reaction can also be used to form biaryls to link two aromatic rings together. Here's an example of that from a reaction we did in my lab about 15 years ago now. You'll see we used potassium carbonate as our base instead of sodium hydroxide. This DPPF is just an abbreviation for a ligand that is similar to triphenylphosphine. Okay, but you can see that you can form very hindered carbon-carbon bonds in this process. Our product here has 3 substituents in ortho positions to where this carbon-carbon bond is. So that's fairly hindered. It shows the power and the utility of the Suzuki reaction that it's able to form such a hindered bond. Okay. Just briefly on the board, we'll show you a couple of ways that we can make the boron reagents that are used in the Suzuki coupling. We can perform a hydroboration of a terminal alkyne, and the boron adds to the end of the chain. It's a syn addition. The boron and the hydrogen are cis to each other, so we would get a transalkene in that case. And then we can also perform a substitution reaction on boron. If we have 3 ethers attached to our boron, and we use a very strong nucleophile, such as an organolithium, we can actually displace one of those ether groups, and we can generate this aryl borane shown here. So we're not going to go into great detail there. We'll just show you those couple of examples. What we'll show you here at the end is the mechanism of the Suzuki reaction. And this mechanism, just like the Heck reaction, when we're showing mechanisms of palladium catalyzed reactions, we're not going to use curved arrows. Many organometallic reactions are not well suited to curved arrows. Curved arrows are only useful if they help you understand what's happening. They don't help you as much with organometallics. So what we're going to do is we're just going to give a name to the individual steps. You would have to write a name over the reaction arrow and not write curved arrows. Okay? So here's what's happening. Step 1 doesn't really count. It's just dissociation of 2 ligands. And so we would just understand that those ligands are continually associating and reassociating. We would just start with a palladium catalyst with 2 ligands. That's going to collide with our aryl or vinyl halide. It's going to undergo oxidative addition. Okay, we talked about that. That's going to give us this happier palladium complex that now has 4 groups on it. Now that we have these 4 groups, we're going to have to switch out the halide for our other R group. And the way we do that is in part 2 by a process that needs a name. They should have given you the name, but sadly they didn't. It's called transmetallation. Transmetallation is when a group swaps positions from one metal to another. Now, boron is not really a metal, but it is a metalloid. It is on the border between metals and nonmetals in the periodic table. Okay, so we would consider it a metalloid. So if an R group switches positions from boron to palladium, we would call that a transmetallation. But it can only do that after the base attacks the boron. This boron is highly electrophilic. It's neutral, but it has an empty orbital, only 6 electrons, 6 valence electrons. So hydroxide attacks the boron, giving us a negatively charged boron species with 4 groups on it. Where have we seen that before? Negatively charged boron with 4 groups. Borohydride, BH4-. And what that did is it transferred one of its hydrides, an H-, to a carbonyl group. So this R group is going to bear part of that negative charge, and it's going to get transferred to the palladium, and it's going to displace the halide. The halide is a good leaving group. This isn't really an SN2 reaction, but you can think of it like that. It helps us understand what's going on. This nucleophilic R group attacks the palladium, displacing our halide, giving us a new 18-electron complex that now has 2 R groups on it. Okay? Now that we have those 2 R groups there, we're primed for reductive elimination to occur. We generate our carbon-carbon bond. That gives us our product that has either the alkenes linked together or the benzene rings linked together or some combination. And finally, you'll notice we've regenerated our catalyst, our palladium with 2 ligands, our 14-electron complex that can go back and do the oxidative addition. Any questions? All right. Well, you can take some time to digest that then over the weekend. Hopefully, we'll see you tomorrow at the review on Zoom, and we'll see you in class on Monday.